So the only acid-base definition we've talked about to this point is the Arrhenius definition. Arrhenius acid is something that produces hydronium. Arrhenius base is something that produces hydroxide. But these two scientists kind of simultaneously came up with the same definition that expands acids and bases a little bit. Their theory is essentially, or their theory was, that an acid would be anything that gave up a hydrogen ion, an H+, and a base would be anything that accepted an H+. So if you look at this reaction down here, we have an NH3 on the left-hand side of the equation, and you can see that it's accepting a hydrogen, an H+, and becoming ammonium, right? This is actually called ammonia, and we already know this is called ammonium. So it's becoming a hydrogen or proton acceptor. And so by the Bronsted-Lowry definition, this NH3 would be a base because it's accepting a proton. And then the hydrogen carbonate ion would be an acid because it's donating or giving a proton to the base. The way that we recognize that what's happening, for example, to the ammonia is we look at the other side of the equation and we look at the thing that it differs from by just one H+. And of course it differs from ammonium by just an H+. And we actually refer to this as its conjugate. Okay? And actually these two are conjugates of each other because this is a two-way reaction. So the NH3 gains a hydrogen, gains an H+ to become an H4+. But since this arrow works both ways, you can also say that in the reverse reaction, NH4+ is losing or donating a hydrogen to become NH3. So they are conjugates of each other. And NH4+, because it loses a hydrogen, would be labeled the acid on the right side. And of course that means the carbonate is accepting and therefore is the base on the right side. So we have an acid and a base on both sides. We have two sets of conjugates, and we kind of connect them with arrows just to kind of show the relationship and that we understand that they are related to each other. And then the other thing that we can talk about is how strong and weak these things are. So I don't have any fully strong acid or base according to the list that you've been given in this reaction. So there's nothing that ionizes completely in water. But among our weak acids and bases, there is a varying strength as well. So, for example, if I have two acids in this equation, in this case, hydrogen carbonate on the left side, ammonium on the right side, are both acting as acids. If I were to compare these two in terms of strength, one, of course, is always going to be at least a little bit stronger than the other. And this table here, you don't have to copy this, but just to kind of look at it, this table actually shows me, and it shows relative strength of acids. We have our, of course, 100% ionized acids at the top, and there's a few missing up here from your total list, but you get the idea. And so we have our really strong acids at the top, and then we are weaker and weaker as we go down. So if I compare my two acids in this equation, hydrogen carbonate is right here, and ammonium is just above it. That means that ammonium relative to hydrogen carbonate is at least slightly stronger. So I'm actually going to label that SA, and I'm going to label the hydrogen carbonate WA, meaning stronger acid, weaker acid, just relative to each other. Okay, so the stronger acid is better at doing what acids do according to Bronsted-Lowry, which is giving up a proton. And the hydrogen carbonate is a little bit, not as good at giving up the proton. And then if I look at carbonate versus ammonia, well, they're over here on the base side. So here's ammonia, and here's carbonate below it. The bases actually work in reverse. So the strongest bases are at the bottom of the list. And so that means that carbonate is a stronger base than the NH3 is. So we have carbonate stronger, I should say, and ammonia weaker. All right. So what does that mean? It just means that these two guys on the right-hand side are better at doing what acids and bases do, which is giving in the case of acids, and receiving, in the case of bases, a proton, right? So if you think about it, what that means for our equilibrium system is if these guys are better at transferring that hydrogen and becoming the reactants, becoming these guys on the left, that means at equilibrium, there's not going to be as much of our product. And it means that if we were to write like a KEQ for this equation, a equilibrium constant expression, we'd have a really low number because the reverse reaction would have happened more by the time we reach equilibrium. The other thing that we can tell from this is if you look at our really strong acids, like HCl, its conjugate, basically it's a really strong acid, and what that means is it's really, really good at giving up a hydrogen. It ionizes completely. When it comes into contact with almost anything, it will give up a hydrogen and become Cl-. And the relationship here is the stronger the acid, the weaker its conjugate base. And the reverse is actually also true. The stronger the base, like a really strong base, CH3 is going to be really good at accepting hydrogens, and once it does so, it's going to become a really weak acid. And the reason for that is you can think of it in terms of stability. If HCl is really good at giving up protons or hydrogens, the reason is once it does that and becomes Cl-, it's much more stable. It's lower in energy, and that's kind of a state that it wants to be in. And so once it's lost that H+, once it's become Cl-, it's very unlikely to re-accept an H+, because accepting an H+ puts it in a higher energy state, puts it in a less stable state. So when we look at conjugates, we can always think about, all right, so if HCO3 is a relatively weak acid, that means it can give up a hydrogen, it has the ability to do that, but it doesn't do it all the time because it's fairly stable the way that it is.